has to do some paperwork, so he said he will be a little late. And there are still some students probably setting up of the system. Now what's happening here?
Just to cancel.
Oh.
This one
Cancel. Cancel. So, and then we looked at the once we acquired the images, we looked at the extracting of the features, and once we have the features, we do the classification and development of the classifiers. Today's lecture, if you remember, for the day 4, I had planned to talk about the imaging in visible spectrum. We have talked quite a bit about the visible spectrum because the examples we were using mainly came from the visible spectrum. Some of the images, even yesterday when you were trying in the tutorial, also came from the visible spectrum. Then we would talk about the hyperspectral imaging, thermal imaging, and X-ray imaging, and what purposes they can serve, and how to use those systems. I think my presentation when I was working on last night is probably not in that sequence. I think the X-ray maybe before, and the thermal, and then hyperspectral is probably towards the end. But those are the 4 areas we would look at today. So looking at the visible spectrum, you have looked at the spectrum, but when we are talking about the visible spectrum, if you basically focus on that, we are talking about 400 to 700 nanometer is the visible spectrum, and you are acquiring images in that region. And when you look at that visible spectrum, this gives you little further details on it, that it is made of the 7 colors. When you use the prism, you can split the visible spectrum into 7 colors, and those colors are then represented by the narrow ranges in that visible spectrum. So the red, for example, is covered from 625 to 740 nanometers, and violet on other end of the rainbow or the spectrum is covered from 380 to 435. And that's why basically it's referred to as visible spectrum for 400 to 700 nanometers, even though when you look at the range, it seems to slightly go above that. Now that another thing keeping in mind, visible spectrum, on other side of the visible spectrum is the ultraviolet, UV. So this right here is the UV spectrum, and this is the infrared spectrum on the right side of the red. And UV is not very commonly used for image processing, but it's certainly used for fluorescence, detection of the fluorescence. So sometimes some of the microbes would fluoresce under UV lights, and then if you use the UV light, then you can do the imaging by taking the images using the UV camera or photospectrometer, but not very commonly used for image processing. IR, on the other hand, is used quite a bit because particularly near IR, which is referred to IR close to the red color, and far IR is referred to the farthest from the red color. So NIR is quite often used, and I think all of you, particularly those in the food science and even in ag engineering, would have covered using the NIR for measuring the characteristics of the food materials. Okay, so then again refreshing that the cameras typically there are 2 types of cameras: area scan camera and line scan camera, and again we have talked about that example. And the system still consists of, basically you need a camera, you need a stand for the camera. Camera usually would have proper lenses to it, you need proper illumination, and when you start reading the literature, you would see many people try to design many different unique way of presenting the light on the sample, and that's where the illumination chamber design comes into play. There's basically, sometimes you can even say the trial and error doing the uniformity test, and then need the computer system for processing the images. Now the resolution of the area scan cameras, typically they are 640 by 480, and there are some cameras also have the resolution being 1024 times 1024 pixels. So if you look at that, that would give you roughly, when you do the multiplication, that's how you get the megapixel, which is giving the area of the image. The line scan camera, I also showed you this earlier. The one thing which I think I did not mention in the line scan cameras was that typically the number of sensors in a line, because line scan camera has the sensors in a line, and those sensors could be as few as 512 to as many as 12,088 pixels. So why you would use the larger elements or larger number of elements? Typically what happens is, depending on the, like especially if you're doing the continuous processing and your objects are moving continuously, depending on the width of the belt, you may want to use larger number of sensors in the line, because when you're taking the images, and then it would give you a better resolution on the imaging surface. Because if you are using, for example, 512 sensors and your belt is quite wide, you would have to lift the camera up, then the size of the pixel on the surface of the object would become very small, okay, or would show up as large pixel size. It would give you less sensitivity in that area. So then you might better buy larger pixels, and then you can see much wider width. And they are not necessarily that you can buy. They come not necessarily you can order them that give me a camera with 1,000 sensing elements, or send me a camera with 2,500 sensing elements. They are pre-made, so you would have to pick basically which sensing element range you want to use for your particular application. Also, the sensing applications of the visual spectrum, almost I would say anything you can think of in the area of assessing the quality of the raw or the processed food, visual spectrum research has been done, or people have at least investigated the idea. So there are many publications in the field of visual spectrum applied to the monitoring the quality of the food. Quality of the food. Our own lab has done a lot of work on the machine vision for the grain quality inspection. So I have given you just few examples here. For example, Majumdar and Jayas publication in 2000. He did PhD in the machine vision area with the group, and looked at the morphological, color and textural features for identification of different grain types, and received the accuracies more than 90% in identifying correctly the grain types. And the grain types he was looking at was wheat, barley, durum wheat, rye and oats, for example. If you introduce more grains in that, like for example canola or rapeseed, if you introduce soybean, I think the classification accuracy would probably improve rather than decrease, because the wheat and barley and rye are the closer together as a family, and if there are less errors in that case, by introducing contrasting grains, you would improve the classification accuracy. Similarly, work has been done on looking at the features for identification of the foreign material in the grain and the dockage components in the grain. And the dockage component, as you would know, is typically the dockage is defined as anything present in the grain sample which could be removed by sieving, and then whatever is left after sieving in the grain is the foreign material. So for example, if there was a kernel of barley in wheat sample, barley is a very good grain, and but it would be considered a foreign material in wheat sample. Okay, or even the rice kernel, or even the soya bean, and anything which stays with the grain after cleaning, mechanically cleaning, would be considered as a foreign material. And dockage is the material which is then separated by the sieving, and be able to identify that dockage using the image processing. So that's and as you can see, the number of years we started the work on the image processing or machine vision, I think probably 1991, when we had would be the first project which was done on the machine vision. So I've been working almost 25 years in that area. And so that's why some of the publications listed there are older publications. And then, so in case of Nair, who was a master's student, he used the morphological and color features to identify Dockage components. And Polyval, who did PhD with me a little later, used the morphological, color, and textural features to identify Dockage components, and got the accuracies were less for the irregular shaped Dockage material. So like irregular shapes could be, for example, if you look at the wheat chaff could be very tiny wheat chaff in the grain sample to very large size. And so you couldn't, like the features become very difficult to do the characterization. So when you're dealing with those kind of materials, you would get less error because even the training sample, you can't have a very consistent training sample. And even though you would train using range of particle sizes, but still when you look at the real sample, you would get some errors, whereas in the well-defined objects, the classification accuracy was over 90%. And in many of these studies, as we kept improving the algorithms, the accuracies did reach over 98, between 98 and 99% classification accuracy, which is quite high. Okay, so keeping in mind the visible spectrum, the classification of the objects or assessing the quality has been done almost fruit, any type of fruits, vegetables, processed foods, even the intermediate steps in the processing. So many applications are there in the literature of the for the applications of the visual spectrum. So then when you're designing a grain inspection system, so naturally you would need a camera to do the inspection, and then you can use, in this example shown here, is that line scan camera, and then you can design a fully automated system where grain would continuously flow. So this is basically using our line scan camera. And then, so you could put your bulk sample in the trough there, and then if you vibrate that trough, you would have basically is the kernels would fall on the belt, and there are two belts which are running at a differential speed, and by running them at the differential speed, then grain kernels get separated and individual kernels get presented to the camera. So this is showing the both belts now. So the grain is falling from the first belt to the second belt, and on the second belt they get separated, and then you take continuously the images. So you can analyze samples on a continuous basis, and then once you take the images, you can then again be talked about to then extract the features, do the classification and quantification. Yeah.
If you have thin layer, then it will work. When we have large quantity of sample, then how to?
So if it is the, no, that's a good question. So if it is the large quantity of samples, so first you have to decide that you want to do the assessment based on the bulk material. So in that case, if you have your images would be coming from the bulk grain, just like I showed you the picture of the singulated kernels versus bulk sample. So like if it was a moving belt and you had a one or let's say 1 centimeter deep or 1 inch deep grain kernels were moving on it, and you start taking the images, you would take the images of the bulk samples. So you be making the decision then, whatever decision you can make based on the bulk sample. So you would take, for example, color features, and the textural features would be the only thing you can extract, not the morphological features. For morphological features, you would basically have to devise a system so that the kernels are presented in a singulated way or individually.
And
yeah.
The rice water stock, they have launched on rice color sorter.
Yeah.
It is working on the same principle?
It's working on a, I would say, in concept, yes, the same principle. But what it is working on is in this case, as we talked about, that you can extract lots of features. So 130, 150 features you can extract from individual kernels. In the rice sorter, what they are basically using is the single color, and they are using the mean value of the color as a feature. So in that case, their sensing element basically is sensing one feature, and based on that one feature, they are making the decision. So this concept is the same, because if you look at the Satake sorter, and I think I have a picture on tomorrow's lecture. In Satake sorter, the kernels are dropping in the single layers in the fluted rows, and then the individual sensors are looking at each kernel. So every kernel passes that sensor basically, and when it notices a different mean value of the color. So if you set, like for example, you were looking at white rice, and you can set the white rice should give you the reflectance closer to probably say gray level, let's say 200, and then anytime the sensor would see anything different than 200, triggers that it is not rice kernel. So that's the principle that Satake sorter is using, but the idea is the same. Another thing I want to point out is, like, usually when you are collecting the samples, and we talked about having the representative sample, and once you have collected the representative sample and you are doing the analysis, you are not analyzing very large quantity of the grain. You are analyzing, typically your sample size could be down to about half a kilo. Now even half a kilo are a lot of kernels, so presenting them in a singulated way, taking the images, analyzing, it still would take time. So sometimes using the Boehner divider, you can divide even further, and you can go down to probably about 100 gram sample, and then you can present them in a singulated way. You can also do that singulation by manually presenting the sample, and a lot of work has been done by manually putting the sample, but that's not, then automation is not possible. So you basically would need a line scan system and continuous movement of the grain kernels. So this is on the right hand side, the images where as you can see on the second belt, it shows the kernels are separated by just mechanically having the differential speed on the two belts.
One more question. For example, I am sorting the oranges, right?
Yeah.
And we have image analyzer, and we have identified that this is the rotten orange, right?
Yeah, yeah.
Can we have a system that when we identify the rotten orange, and it automatically gets separated or dropped?
Yeah, yeah.
Can we do that?
Oh yeah, that's done.
This is actually, otherwise, we will identify.
No.
But
So
if we can identify orange, then we should.
So there are many different ways you can do that. So like for example, if you have a single oranges coming in this line, and as soon as you identify the rotten orange or defective orange, and you can have a little piston come out, like so we would have to design basically mechanical system. So oranges, maybe they are separated, let's say every 5 centimeter. You notice this, take the image, the time you would do the analysis of the image, and based on that you would say this is rotten or good orange. In the meantime, the orange may have moved another half a meter. So whatever distance it moves, depending on the time it takes to do the analysis, then at that point you can have a piston which would say this is a rotten one, and it just kicks it out. And then that's how the system would work. So precise calculation. So if your algorithm, for example, takes longer, then your piston would have to be further away. If your algorithm can do instant decision, like within a microsecond, then maybe it could be just down a few centimeters where you can have the piston to push it out. So you can do.
Similar happens with the sorting and grading unit of agricultural products, like where they are passing through conveyor belt, and when they are falling on a conveyor or something belt, there is a something like which push a
piston. Either air, depending on. Yeah. So there are typically two systems are used. Either it's a mechanical piston kind of arrangement which pushes it out, or sometimes air jet. So if especially if you're dealing with the fruits, air jet would not be feasible because the amount of force required would be very, very large. So you would use probably mechanical system. But for grain, you can use the air jet, for example. Okay. Any other questions? And that's where I think the engineering part of the design comes into play, is because you have to figure out the speed of your belt, You have to figure out the image analysis processing time, and like if you change the processing time, like you improve your algorithm, you would have to then make sure the piston location get adjusted, otherwise it would be kicking out a wrong product. So that's where the modification would have to be done. So once the systems are designed for industrial use, they really very rarely would then try to improve it, because then the other part have to be changed simultaneously. Okay, and then this basically completes that image processing of the continuous movement of the kernels required. And these are the images of the simulated kernels. So like in this image, if you see, there are even the differential belt system does not separate everything. Like on the wheat image, you see a lot more separation. I don't know if it's easy to see, but in barley, the two kernels here, these two kernels right there, is still touching. Okay. So even with the mechanical separation, that doesn't happen. And then what is used in that case is, because if the two touching kernels are there and you would do the segmentation, it would now have a funny shape. So the system cannot recognize this barley or wheat or anything. So what is done typically is that you then use the algorithms to separate these kernels, and there are many different ways where you can do that separation. And in our group, there was initially a student looked at the mathematical morphology, which is a field in itself, or ellipse fitting, and using region growing and sinking, you can then separate the touching kernels, and then you can get pretty close to 100% separation, and that means you can analyze all the samples. Okay. So any questions on the visible spectrum? Because we have been using the visible spectrum as an example for many discussions over the last 4 days, so I didn't put a lot more images. But keeping in mind that visible spectrum has been used for almost any material you can think of in the agri-food industry, whether it's in raw form or processed form. Okay. Any questions?
Good. I don't know whether we, up to what level we separate the wheat grains.
Like in,
for example, if the diameter is maybe 3 mm diameter is there, or 3.5 mm diameter is there, right? The width of the grain. Up to what extent we separate or identify the grains?
okay, so and I don't know if I have this, not on this one. So to give you some examples of so when we did the identification of the different types of grains, so like wheat, barley, rye, oats, in that case classification accuracy was pretty close to, I would say, 99.6, 99.8%.
Okay, good.
Okay, so that kind of class accuracy. When we were analyzing the wheat classes, so in that case we are analyzing soft wheat from the hard wheat, spring wheat from winter wheat. So there are 8 classes in Canada, 8 wheat classes. And when we were doing the class identification, accuracy still was pretty close to probably 96 to 98% in the class identification. So so if somebody, and as you would know, and I think that all of the people who are in the cereal science would know, if you had a hard wheat which is used for making the bread, and you have a soft wheat which is usually used to make the biscuits and confection items, and if those two get mixed, you can see the loaf will not come out very good. You will not have a very good bread, and then on the same time your confectionery items would not look very good, or would not taste the same.
Actually, why I was asking this question, because usually we want to know, we have the hailstorm damage, right? We want to know what is the difference between the sound grain and hail damage. So we are always interested to know the quantity of that. My class will try.
No, that's good, that's good. So in that example, like in that example, the question you're asking, so for example, frost damaged kernels, I would say image processing or machine vision, and even just in the visible spectrum, probably could identify them with a pretty close to 100% accuracy because of the changes which would occur because of the frost damage in the kernels. Because there would be significant differences in the features to do that identification, and should not be an issue. Yeah.
So, is there any possibilities to find wax coated apples through visible spectrum of image processing? Because its color features and texture and morphological features are maybe almost same. Is there any possibilities to find wax coated apples?
Yeah, like so you are saying whether you could detect whether the apple is coated with wax or not coated with wax. The only possibility, like certainly there may be a slight difference in the color features because of the wax coating. The reflectance may be different. So again, I would say you would have to try it. So that's possibility that maybe there is enough difference in the color to be able to identify. Another thing wax coating might do is change its textural features. Okay, so you would have to basically present both samples and extract the features, and then do the classifier and see if there is enough difference. If there is not difference in the features, you really can't. So it all would depend as if there is a difference in the features. Yeah, it would be difficult because it's the thin layer is so thin. The only thing it might change would be the reflectance, depending on the shininess of the wax.
Yeah, only way would be that you use some organic solvent like a copper or wax.
Yeah.
So you have to solventize and
Without using that one apple, we can any possibilities without touching that apple or through image processing or any other.
it would be difficult because it is a transparent layer, you know, it is very difficult.
Yeah. Now the one thing I think, like when we go through the hyperspectral imaging, with the visible spectrum, it may be very difficult to do because we are relying on the 400 to 700 nanometer range cameras. When you go to the hyperspectral imaging or NIR imaging, then again, because there you are looking at a few millimeter depth of the sample, and by having the layer of wax, it's possible that it might affect the spectral characteristics. And again, without trying, it's hard to say. You would have to try that. If it creates enough difference, then you'll be able to identify. Okay. Any other questions?
Using X-ray and another techniques related, we can also determine the internal quality of
Yeah, so that is coming. That's right, and that's what the X-rays are used for. The next we are going to cover the X-rays. Any question on the visible spectrum? Okay, and as I said, like they have been used for any raw material. So the classification of the grading of the fish, for example, even grading of the eggs, detecting cracks in the eggs during the processing, or like even when you do the separation of the egg yolk from egg white, and then to detect the cross-contamination, that how much egg yolk is left with the egg white during the automated processing. The visible spectrum has been used for making those decisions. Okay. Moving along then, the X-rays. So as you can see on this graph, the X-rays are basically before the gamma rays, and the way you produce X-rays is typically you have an anode and a cathode. You basically the cathode would generate the electrons, which then are attracted by the anode. It strikes the anode, and the X-rays are produced. So that's how the rays themselves are produced. So the X-rays basically are quite powerful rays. So if you look at the X-rays, if you go back in time, they were discovered by Roentgen in 1895. So X-rays has been around for quite long time. They are electromagnetic radiation. That's why the spectrum says, and it lies between the ultraviolet rays and the gamma rays. So that's where the X-rays are situated in terms of their position on the spectrum. And the wavelength of the X-rays lies in the range of 0.01 to 10 nanometers. So compare that to the visible spectrum, where we are talking about 400 to 700 nanometers. You are now down to 0.01 to 10 nanometers in terms of the wavelength, and the corresponding frequencies then of the X-rays would be from 3 to 10 to the power 16 to 3 to the 10 to the power 19 hertz. So these are the cycles per second. So when you look at the X-rays, and the energy range for the X-ray spectrum would be from anywhere from 100 electron volt to 100 kilo electron volt. So that would give you the range of the energy of the X-rays. X-rays are produced, and I already mentioned, in the vacuum tubes by which contains both cathode and anode, and vacuum tube is enclosed in a glass or metal envelope, so that X-rays are contained in that envelope. Okay, come on in. Yeah, sitting there would be hard to see the slides, but he might be able to turn on the project on the. Oh, okay. But would it then project from the same computer ducts up there? Okay, okay. Okay, it will take a couple of minutes to get the system set up. What's the time? Almost an hour? Waiting for your screen to come down. So the group which has joined is undergraduate students or graduate students? Oh, okay. It's not fully set up all the time. You just flick one switch. You have to reconnect it. No, I think he was saying it's connected. That's what he was saying. So we will see. So
You have to put PPT there also.
Oh, okay. Okay. Yes, copy here. It's the fourth day 4. Yeah. Okay, so because many of the students have joined late, I will go very quickly from the beginning and not take the same amount of time though. Okay, so today's lecture we are covering is the image processing or looking at the samples in 4 spectra in the visible spectrum, which is a 400 to 700 nanometers, which is what the human beings see. Then we will look at the X-ray, thermal imaging, and hyperspectral imaging. So this is the visible spectrum. If you look at the overall spectrum, visible spectrum, 400 to 700 nanometers. You have to keep an eye here. Yeah, you have to keep an keep an eye on this screen, and then you have to advance when I'm advancing. Okay, and then when you look at the wavelengths of the different colors in the visible spectrum, this slide basically gives you that the ranges of the wavelength for each of the colors you would see in the visible spectrum, or I think in the rainbow would be the one you are familiar with. This is just the camera system, which basically for visible spectrum imaging, you require a camera, you require illumination source, you require some way to stabilize the camera. You would then, camera would take the images, then you need a computer system to basically do the analysis of the images and do the classification of the objects. This is the example of an area scan camera, and they come into two different sizes in terms of the pixel size. And nowadays, I would say more and more improvement has been happening in the cameras, particularly with the advent of the digital cameras, and you can get very high quality digital cameras nowadays. This is the area scan or line scan camera, where the object is moving and camera is taking the picture in a line. So when you have the object moving and then more lines you collect, you basically then get your two-dimensional image. And in the line scan camera, the unique thing to keep in mind is the sensing elements which take the image could range from 500 to almost over 13,000 sensing element, which means you can cover the wider belt or narrower belt, and you still get the same resolution or same quality image. Applications of the imaging in the visual spectrum, I would say it has been applied and has been used, and I would say from both research perspective and many industrial applications to evaluate the many or almost all raw food materials as well as food materials. And in the bottom of that slide are some of the examples from our own research group, where we were able to identify using the morphological, color and textural features different cereal grain types or the dockage and foreign material in the grain, and then get quite high accuracies. Then if you want to design an automated system, you would typically use a line scan camera for automated system, where you would have the camera which is positioned at one place and taking one line image at a time. And by using the belt, where the grain would be moving on the belt, you create that relative motion, and that gives you the second dimension of your images. This example shows you by using two belts and then having a differential speed, you can this can help separate or singulate the kernels, so individual kernels get presented to the camera. And then this is just showing you that you would put the bulk sample in the trough. It moves on the first belt, then it drops on the second belt, and when it drops on the second belt, and the second belt is moving at a higher speed than the first belt, it basically separates those kernels. And then separated kernels get presented as individual kernels, which camera is seeing individual kernels. Even though you put a bulk sample in the trough, you get individual kernels, you take the images, and then do the classification. In real life, even with the dual belt system, all kernels do not get separated. So there are some kernels, like on this example, some barley kernels are touching on the left-hand side image, whereas the wheat kernels in this examples are all separated or presented individually. So you can extract the information from these singulated grain kernels and then do the classification. Then we want to talk about is the X-ray system. So X-rays are between ultraviolet and gamma rays. And you can use the X-rays for exposing the samples, and then images acquired from the exposing the samples to X-rays, you then do the analysis of the images the same way as you would do the analysis of the images from the visual spectrum. And that's why we covered the analysis parts at the beginning. So we conducted the feature extraction and analysis part, because feature extraction would be the similar idea. Now only basically you are changing is how you acquire that image, whether you use the X-ray or using the camera. So X-rays were invented by Roentgen, and sometimes they are also referred to as Roentgen rays, although X-rays are easy to say, so nobody probably calls them Roentgen rays, but invented in 1895. And they are magnetic radiation, as I showed you in the electromagnetic spectrum between ultraviolet and gamma rays. And the wavelength of X-rays lies in the range of 0.01 to 10 nanometers. And then if you convert that wavelength to by the lambda 1/lambda ratio, They basically gives you the frequencies from 3 to 10 to the power 16 to 3 to the 10 to the power 19 hertz or cycles per second. And the equivalent energy of the X-rays then could be somewhere between 100 electron volts to 100 kilo electron volts, so basically up to 1,000 times that. Okay. Then X-rays are produced in a vacuum tube where you would have a cathode and anode, and typically the electrons are produced from the cathode, attracted by the anode, and when they strike the anode, that's when the X-rays are released. And typically you would need a very good glass or metal container so that the X-rays don't leak, and because the people being exposed to the X-rays can have, certainly it has been shown that a significant amount of exposure to X-rays can become carcinogenic. So there is always a protection bore by the people who are working around the X-rays. And then even when you go for medical imaging or for X-rays for medical purposes, the person who is taking the images usually would go behind the wall or behind the glass enclosure when they would turn on the X-ray system, because the patient we need to be exposed to the X-rays, but not the person working with the X-rays. Okay, and this is where you join. Then the X-rays have been used in the agri-food industry for detection of defects, which could be maturity defect or damage caused by physical or biological changes or the foreign materials. They have been used as a non-destructive method for evaluating the quality. The main working principle of the X-rays is that when you pass X-rays through an object, the X-rays are attenuated or changed based on the density differences in the material. So if you had a denser material, X-rays would be blocked more. So then on the detector side, once they go through the material, you would have a different image or different reflectance value or transmitted X-rays. And then the softer side would give you difference. So it basically uses the density difference, and that's why they are used quite often to detect the materials having different densities. And the most common example you would have seen of the X-rays is when you go to the airports, all of your luggage get X-rayed, and in that case they are using what's referred to as hard X-rays. And hard X-rays have a power to penetrate through larger or deeper materials. Soft X-rays, on the other hand, are used, or the penetration power of soft X-rays is less, so they are typically used for the biological materials or agri-food materials. So high energy, hard X-rays have high energy and more penetration power, and those are the ones which are used at the airports. In the medical imaging also hard X-rays are used, and soft X-rays being low energy and less penetration power are used with the biological materials and particularly the agri-food materials. Some more details of the X-rays which I have already mentioned. So here it is looking at the X-rays range from 0.1 to 10 nanometer and corresponding energy. Soft X-rays have the longer wavelength, lower energy and low penetration power. Hard X-rays have the shorter wavelength, high energy, and that means then they have therefore have high penetration power. Soft X-rays are suitable for agri-food products because of their low penetration capacity, and hard X-rays are suitable for because of their high penetration power, suitable for medical imaging, airport security systems, and even in the food industry. When you are looking at, and I will show you some examples, when you are looking at, for example, if you want to detect the bone and you are producing a boneless, let's say chicken breast, or you are marketing as a food processor that your chicken breast is boneless and does not contain any bone, because if you market as a boneless and it has a bone, somebody can chew on it, can damage their teeth, and then they are the one who would sue you. So you want to make sure that any material you are packaging doesn't have the bone. soft X-rays would not be able to penetrate the thickness of the chicken breast. So you would have to use the hard X-rays to detect, for example, the bone in the boneless meat packaging. And that could be said of the ground meat, and you don't want to have that. Sometime in the processing, and that's why workers are not allowed to wear the jewelry and are not allowed to have the metal parts. But even then, the processing unit itself, metal might come off, or the nut may come off and end up in the meat packaging. Before it goes to the consumer, you want to inspect that, so that's where you would use the hard X-rays because of penetration power. Okay.
So hard X-ray doesn't have any harmful effect, additional harmful effect than soft X-ray?
No, it doesn't have on the product itself, but if you expose the human being continuously to the hard X-rays, I think there's a lifetime limit of there's a lifetime limit you want to expose the person to the X-rays. The biomaterials won't have because I think the material is already in a sense dead. So all you are doing is quickly passing it through the X-rays. You are basically detecting is the possibility of the contamination of the heavier materials in the soft tissues. Yeah.
Doesn't have any texture effect?
No, because you are not exposing very long. Like it's almost like millisecond kind of exposure to quickly see what's present in there. Okay. Soft X-rays have been used for defect detection in fruits, vegetables, and grains, and I will show you some examples. So as an example here, to detect a hollow heart in potatoes or detect the split pits in the peach, soft X-rays images were acquired by using soft X-rays. And once you have the acquired images, now in this case you can say the person who is doing the inspection can look at that and right away know that this potato has a hollow heart. Or you can design the algorithm as we talked about in the last 3 days, extract the features, and based on that you can say if you see this kind of pattern, that means it has a hollow heart, and then you can do the automation and reject based on the automatically detecting the potatoes with hollow hearts. Now why that becomes a problem is like especially for the French fry processing. You don't want to have that because your French fries would not come out of the right square cross section. Now at the household level, I don't think hollow heart would make much difference in terms of the quality of the preparation. But at the house, even when you bring the potato with hollow heart and you cut it and you see the hollow heart, people still question that is it of the right quality or not. Because they could say that why that the hollow part got created. Was it created by insects which have moved out, or larvae? But it is created during just in the growth process. The hollow heart is created in the growth process, and there's no truly there's no damage, but people still would reject that. So that's why you want to detect these ahead of time before it goes to the consumer. A split pit in the peach, the same thing, taking the image and then developing the algorithms and classifier. You can do either automatically or you can also do using the human person, but it aids the human being in making that decision, because looking at the potato or peach from outside, you would not be able to tell whether it has a hollow heart or it has the split pit. Okay. Other examples I have mentioned the hard X-rays, the metallic or non-metallic contamination in the food products. So metal, bone, glass, stone, plastic, all those can end up in the food product. So you can use the hard X-rays for that purpose. And in this particular case is the example of the image of a chicken fillet and trying to detect the, I think it's the bone fragments, and you can see them even with your, I don't know if the light reflectance is causing too much difficulty here. Yeah, there's too much light coming here, but there are there is a bone, tiny bone, and it can detect very small size bones, like don't have to be large bones. So I think these would be few millimeter in length. Can you see on that one better? Okay. It's too bad that the light intensity is too bad. So this basically is showing you the bone fragments, so where the arrows are. Okay. I don't know if you right there. So this is the size of the bone here. Okay. X-rays. There are two different ways you can present the X-rays. Like in this case, this shows you the different way how the X-ray beam could be directed on the food product. So a single horizontal beam, or you could have a split dual beam X-ray, or you can have a cross, basically the two beams with the two separate generators, and do a cross. That means you can look at the two different planes. And many other possible arrangement could be, is another possibility is, depending on the material, you could also have the beam going from the top, for example. Okay. So again, looking at the insect infestation in the grains, X-ray, as I said, were invented in 1800. The initial use of the X-rays in the grain industry was to detect insects using X-ray films. So and I think even nowadays, some of the, if you go to the radiography shop to get X-rays done, they used to have a film which they would insert, and then so you would have the X-ray source here, person would be in the middle, and the film would be put at this side, so the transmitted X-rays would be captured on the film, then the film get processed, and then you would get the results. Nowadays, that there are digital systems available, so you don't use the film, and it would basically give you, just like your digital camera that gives you the image, it would give you the X-ray image. But this process is the same. So initial use was in 1932 using those films, and then it was used for detecting of the internal grain feeders such as rice beetle, grain beetle. These are the different insect types which are found in the grain. Maize beetle and lesser grower in cereal grains. Recently, with the real-time digital images you can acquire using the X-ray systems, and with the real-time digital images, again, they have been used for detection of the internal and external grain feeding insects in wheat, and the external feeders, the accuracies about 81%, and for internal feeders, because they are inside, and then you can see the differences, almost 97% accuracy in detecting insects. Okay, and this is the example where in the real time, like X-ray imaging system, you see the kernels are in the middle on the platform, and in this particular example, the voltage being used is a 15 kilovolt and the current of 65 microamp. And see, I don't know if you can see that the bottom is the X-ray tube. So this point here is showing the X-ray tube. This is the way where the X-rays are being generated, being passed to the grain kernels, and the detector is on the top. So you would basically capture the transmitted energy from the sample using at the detector, and that's what would give you the image, which in this case is the example of the sound kernel. So the first one is the sound kernel. Again, if the light was clear, you would be able to see on the rusty grain beetle is one of the insect type. It grows in the germ end, so the top part of this is at very different intensity than the rest of the image. And then in the rice beetle, I don't know if you can see, the larva is developing about here, and you can see with the difference in the larva development. So in the case of again, these images, as you can see from the visual inspection or yourself, if you saw that image, you'd be able to say that, yeah, this has an insect infestation. But if you want to do that automatically, then you would have to extract the features, and in this case, you would have to look at the intensity differences. Probably you can tell the difference, and particularly if you did the textural feature, for example, can separate detect the larva, or you could do the histogram features, because histogram distribution would be different for sound kernel than for the infected kernel. Because when you plot the histogram, you would have different intensity patterns. And just using then the histogram, you would be able to do the differentiation. Okay, so this shows you where the infestation is happening. This is another example of the rice beetle where the larva is growing inside. So soft X-ray imaging has been used from a grain perspective. We have used this in our lab for detecting 5 different types of insects, and the accuracy more than 84% to detect the larval stage, and the pupae and adult more than 96% accuracy. And with that kind of accuracy, then you can design the system. So if a farmer is delivering the grain using a truck, and you take a sample, very quickly you run through X-ray system, you would know that the farmer's grain has insect infestation or not, because of the decision-making time is few seconds basically, or certainly less than a minute. And then you can tell the farmer that you would not accept their grain, because particularly in Canada, we have a Grain Canada Act, zero tolerance for insects in the grain. So if a receiving agent sees a single grain kernel having insect in it, they are not supposed to accept it and reject that grain. The reason is that if you did not detect and let that grain dump in your facility, these insects are going to multiply and you would be infesting the whole facility. And the cost of basically treating that whole facility would be much more expensive than telling the farmer, take this grain back, treat it your own grain, and then you can bring it back later. So the farmer has the responsibility for treating. There are times when the detection doesn't happen, and using particularly the current method, which is a heat-based method, it can take up to 6 hours, and no farmer want to wait 6 hours for making that decision. And the people making the decision are basically doing the visual inspection and try to see if there are signs of insects, and they make the decision based on that. We were able to demonstrate that you could use the X-rays to speed up that process and avoid the treatment of the large quantities of grains, for example. And this is quite high accuracy to be able to detect larvae and pupae and adult stage. Industrial applications. I already showed you one example of the detecting of the bone, and I will show you many more examples of the industrial applications in tomorrow's lecture. But the issues need to be considered in the industrial applications are machine cost, like how expensive is the machine. But what you have to take into consideration is, and I would use the example of the grain, if you spend, and whatever number we want to use, but let's say $100,000 is the machine, and you use the machine to detect the insects before they get unloaded or not unloaded. If you did not have the machine and you unload the grain and it infested your whole facility, treating that facility probably would cost you more than about $250,000. So if you can avoid one infestation of your facility, you can buy $100,000 machine. Okay, so that's why. So when you're looking at the cost, what you have to look at is what you would gain from investing that money. But the machine cost is still people bring that up as a reason why they cannot implement the system. Radiation exposure is another one to the workers, and which I already mentioned. So it has to be built in a facility which is sealed facility, and then at the same time the people running the samples would have to be shielded from that. So if you did the automated system where you were moving the kernels, and then the shielding can be done where the X-ray images are being taken, the rest of the part doesn't have to be shielded. So it can be designed, but the radiation exposure has to be taken into consideration. But currently food industry is the second largest user next to the electronics industry of the X-ray systems, particularly the hard X-rays for detecting the contaminants in the food. It is used for the, has been used for the bulk solids, for the liquids, packaged foods, packed chocolates. First application was the detection of the contamination, and actually it was not even detection, it was more when you are packaging chocolates in a laid out box, it was looking at whether there is a particular type of chocolate did not get put into the box. Was the first application, because where the chocolate was not there, it would show up as a different intensity. And then since then it has been used in many applications. So for example, if you were going to design a grain inspection system using X-rays, similar to the dual belt system I showed you earlier, so you would have the trough or grain hopper where you would dump your sample, vibratory feeder would then move that to the first belt, then to the second belt. X-ray system would basically take the X-ray tube would generate the X-rays. Your detection system would take the images. This is the X-rays coming from top down. So your detector system is at the bottom of the sample. Take those images and then do the analysis. And then basically you can do this on a continuous basis. Okay. Challenges, I think, in the grain inspection system are similar to the visible spectrum. You need to present these kernels on a singulated way, but more so, even if they are touching, you could do the separation using the software. And the reason I think you need to still do the separation here is because if the two kernels were touching, then analysis would be difficult once you're extracting the features. But if you were only using the histogram features and not any physical features, then it would not matter, because 2 or 3 kernels could be together and histogram pattern would still be different between the sound kernel and infested kernel. So in this case, the singularity of the kernels is not as critical as it would be in the visible spectrum. So in X-rays, you could manage that. Ideally, you would want to do that. Other challenge, I think, in the grain inspection system is the acceptance by the industry of the cost-benefit ratio of implementing this system. And currently, actually now, there are the hard X-rays. You can buy line scan systems because that's what the airports use and that's what the hospitals use, the area scan ones. But then the soft X-rays, the line scan systems were not available, but now they are available on the market. So they could be applied to softer tissues as well as the deeper tissues. And I mentioned already singulation of the grain kernels. And the shielding of the X-rays is the issue, because you want to avoid the exposure of the human being, so reduce the high scattering of the X-rays. Okay, so we would then take the break at this time, and then we will cover the thermal imaging and hyperspectral in the next phase. Okay. Oh, tea is not ready? We can continue then? Yeah. Any questions on the X-ray imaging before we move to the thermal imaging system? Okay. Any? Yeah, okay. No, I was just saying, any questions on the X-ray system from any side of the room? No? Okay, so the tea is ready, so we will take a short break, about 15 minutes, and then we will come back and look at the thermal imaging and hyperspectral imaging system. Okay?
MSc and BTech student, please remain seated here, okay?
Okay, doctors, I'll give you another lecture. So I said the doctors are going to give you another lecture.